SwayamPrabha. Digital India. Educated India.
Hi, so what we have done in the last lecture is to describe the ideal Otto cycle and particularly making use of air standard assumption. We will continue our discussion on gas power cycle, which now we are going to describe the diesel cycle. So, diesel cycle is nothing but the ideal cycle for compression ignition engine. In this particular engine, the combustion takes over a long period of time, and hence we consider or idealize this combustion process as constant pressure heat transfer to the system, or constant pressure combustion, compared to the case of spark ignition engine where we consider constant volume. So, this is the only difference between the Otto cycle and diesel cycle. The diesel cycle, the combustion or the heat transfer to the system is at constant pressure. On the other hand, for Otto cycle it is at constant volume. Okay, so let me just describe the 4 processes of the diesel cycle. So, as I said, for the case of Otto cycle, you have this kind of process. Okay. On the other hand, for the case of diesel cycle, the 1, 2 and 3, which is our heat in, is now at constant pressure. So, this has been shifted, or this has been changed from the constant volume to constant pressure. So, 1 and 2 is still the asentropic compression, and 2 or 3 is your constant pressure heat addition instead of constant volume heat addition as was in Otto cycle, and 3 and 4 is your asentropic expansion, and 401 is constant volume heat rejection. Okay, and the corresponding the TS diagram is following. Okay, so 1 and 2 is of course asentropic. This is a constant pressure, and then this is your asentropic expansion, and this is your constant volume heat rejection. So, of course, this means that the volume is going to change during this process 2 and 3. So, the energy balance will also include the boundary work, and thus for the case of 2 and 3 the energy balance would yield this. So, earlier for the Otto cycle we simply used Q in is equal to change in internal energy, and then we replaced the change in internal energy by CV delta T. But in this case the boundary work is involved, and hence your PV work is included, and which essentially means that Q in can be simply written in terms of change in enthalpy, and considering air standard assumption you can simply replace delta H as Cp delta T. Okay. But for the case of 4.1 there is no boundary work, okay, because this is at a constant volume which is same as Otto cycle, and thus your QIT is simply Cv delta T, as was in the case of Otto cycle. Now, your thermal efficiency, the expressions by definition is the same for the case of diesel. So, this is your W net by Q in, or 1 minus Q out by Q in. Q out now includes the same, heat rejection is same as in the case of Otto cycle, but heat addition is now written in terms of Cp T3 minus T2, which essentially means that now we have to include K also, because Cp by K, Cv is K, and thus this expression is little more complicated compared to your Otto cycle. But you can compare it with Otto cycle by first defining a cutoff ratio Rc, which is the ratio of the cylinder volume after and before the combustion process. So, this is going to be V3 by V2. So, if you go back, your combustion process occurring here. So, the ratio Rc is defined as the volume at V3 divided by volume at V2. So, if you make use of this Rc, just to define it a little different from that of Otto cycle, we can utilize this definition and the previous expression, and as well as the definition of isentropic ideal gas relation for the 1, 2 and 3, 4, and we can come up with this relation for thermal efficiency for the diesel engines. And you can see that you have this term which is same as that of your Otto cycle. In addition, you have this term also. So that means your efficiency of diesel engines differs from that of an Otto cycle by only this term which is in the bracket, and this is turns out to be always greater than 1, which essentially means that your Otto cycle efficiency is usually greater than diesel. As we decrease the cutoff ratio, the efficiency increases, okay? And we can consider the limiting case. When the RC tends to 1, the eta diesel tends towards the efficiency of Otto cycle. The typical compression ratio for diesel is more than that of Otto cycle. It's in the range of 12 to 22. And if you increase this compression, of course, the efficiency will be more. So in general, your efficiency of diesel engine is more than that of a spark ignition engine, okay? You can now make use of this information of the diesel cycle and as well as the A standard assumption, and try to solve this problem at leisure, okay? And hope you can practically understand the energy balances and how to make use of energy balance for different internally reversible process which we have involved in diesel cycle. Okay, so as I said, you can solve this problem at leisure, try to understand the diesel cycle practically. So with this I will end this lecture, and the next lecture we are going to undertake Brayton cycle, okay? So I will see you in the next lecture.